Alright, we have this problem of object mass m at initially certain height, which is on this inclined surface. The problem is when we release the object of mass m, it will come to the bottom of this circular part of the track, and it enters in here inside the circle. It completes a loop and it continues its motion on this level surface. Of course, without the object leaving the track inside the circle, there must be some minimum h, the minimum height. And the question is, what is this minimum height in terms of the radius of the circle, so that the object completes its loop inside this circular track without leaving the track. Okay, so this is the problem. What is this minimum h in terms of r, so that during this motion of the object will not leave the track inside the circle. It will complete a perfect circle and it will continue its motion on the leveled surface. Of course, as soon as the object enters the circular track, we know that from the conservation of energy, the object will have its minimum speed right at the top of the circular track. And also we know that since the object has a circular motion inside this track, and at any speed value we can calculate the acceleration of the track, the radial acceleration of the object inside the track. We can find from this the normal force between the object and the track. So since the object will have its minimum speed right at top, we can concentrate on this point, the top point of the circle, and on this point we want that the normal force between the object and the track is almost zero, right? Of course it shouldn't be less than zero, because there is no any negative normal force between two surfaces. So minimum it can be zero if it will continue its motion without leaving the track. Okay, so let's write the total energy of the object first, and since it is starting from this point at height h from rest, it has the total energy, which is m times g times h. And right at top, suppose it has this speed v, and we can calculate this speed v, okay, in terms of this height h and r. So right at this point, we know that since it has a non-zero speed v, and also initially it has the total energy mgh, and also since this point has a certain height from the ground, which is 2r, it is the diameter of the circle, we can write down the energy relation right at this point. So the energy, which is totally mgh, will be equal to mg times 2r, which is the potential energy of the object at this point, plus 1/2 mv square, which is the kinetic energy of the object at the top of the track. And now let's concentrate on the dynamics of the object mass m right at this point, at the top point of the circular track. So let me draw the free body diagram right at top, and this is the object. We will have a force of gravity which is downward. It is the weight of the it is the weight of the object mass, and also on the object we have the normal force N, which is again downward, right? And these are all the forces acting on the object, and right at this point we can now write down the Newton's second law in the radial direction, in this direction. Okay, so if we choose the y-axis, which is increasing y-axis upward, then the Newton's second law right at this point in the radial direction is also the y direction at this point, and the total forces in the y direction is equal to m times the acceleration of the object, but the only acceleration right at this point for this object, which is on a perfect circular track, is the radial acceleration. But the thing is, the velocity is changing downward, and with this choice of coordinate, this radial acceleration will get a minus sign. So it has minus mv square divided by r. And remember, for a circular motion, the radial acceleration and the tangential speed is related by this equation. A is equal to v squared divided by r. So on the left hand side again, we can simply write down these total forces, and the total forces are downward, so they are to be taken as negative, minus mg and minus n. This is all equal to minus mv square over r. So the minimum requirement that this object won't leave the track is that this normal force is equal to 0. Okay, the normal force equal to 0 or larger than 0 is the condition for the object mass, so that it will continue its motion without leaving the track, or without falling in the air. So we get this n 0, and we have plus mg if we multiply by minus sign both sides. Mg is equal to mv square over r, so m's on the both sides cancel. So we have g is equal to v square over r, and the condition for the object so that it won't fall down as it moves from the top part of the circle without falling is that v square must be equal to g times r, or let's say, to be exact, v square should be equal to or larger than g times r. Okay, if it's equal to g times r, then the contact force between the object and the circular track is equal to 0. It is barely touching, that means. So then for the minimum h, we should have this equality, then v square is equal to g times r. So now we are ready to put this v square value in the first equation, which is the conservation of energy equation, and let's do it to find h in terms of r. So on the left hand side we have mgh, and this is equal to 2 times mgr and plus 1/2 m. Now instead of v square we have g times, okay, here g times r. So on every term we can cancel gm terms because they are common. So as a result, we can solve this equation for h. We have 2r plus 1/2 r. This makes 5 divided by 2r, or 2.5 r. So the minimum age of this object initially should be 2.5 r, so that the object moves inside this circle without falling in the air.